All right, let's go ahead and get started. If you're still finishing up your lunch, go ahead and don't be rushed. Go ahead and take your time. But for those of you who are done, let's go ahead and move forward. So I'm assuming that, I'm hoping that most of you got that to run. How many people got it to work? Let me see your hands. Excellent, excellent. Okay, very good. Now that it's working, there's some really fun stuff you can do. Because there's a debate right now in the industry. How many bits of resolution on your A to D do you need to have to do field-oriented control? Well, let's answer that. Let's try like instead of 12 bits right here, I don't know. Let's do something fun. Let's put in 4 bits. What will a 4-bit A to D converter do to this? You can actually see the current waveforms there, what happens when you quantize them to that degree. What's amazing to me is it still works, even with something like a 4-bit A to D converter. Let's try 8 bits. With 8 bits, it looks pretty good, actually. So again, these are just some things that you can play around with the simulation and just see how it affects your design. Let's put this back to 12 bits now. What if I jacked my PWM frequency down to, I don't know, 2 kilohertz? All right. That's also going to affect my sample time of my algorithm now because my sampling frequency of my algorithm is tied into the PWM frequency. Let's try this. Now what's interesting, look at the response of my speed controller now. It's starting to go unstable. And again, it's because my sampling frequency is so low that the phase delays associated with moving that sampling frequency down that low are starting to interfere with my closed loop frequency response of my speed loop. Let's try, let me put it back to something, let's say like 5 kilohertz. 5,000. Okay, that's not too bad. Okay, now you see that we don't have the stability problems. Let's double-click on the motor graph up in the header of that to blow it up. So that's what the motor currents look like. If you want to zoom in on a particular part of the waveform, what you do is you hit click, you hit control, and then left click and drag to specify an area to zoom up on. And you can actually see now the PWM frequency. Now this is really not exactly what it would look like just because you hit control, right click, and that'll zoom you out. Now that's not exactly how it would look just because I have my graph sampling interval is set very low. You can actually specify what kind of resolution you want in your graph. And I've got my graph resolution set really low just so it'll run faster. Let's go through and instead of, let's see here. No, it's not that resolution. So that one's fine. So let's go now to the under System, System Properties, and you see I got my time step set to 1 microsecond. So that's going to limit, some of the resolution of some of the signals that I'm getting just because my whole simulation is running at a 1 microsecond time step. Let's change that to be like 0.2 microseconds. Now when I run it, it's going to take a lot longer to complete because it's generating more points now. Okay. if I zoom up on the current now, well, it still looks not as good as I was hoping it would look, but anyway. Oh, I think it might be because of my sampling frequency is still pretty low. But anyway, the point being is that you can go through and change different parameters in your simulation to see how exactly they fix certain issues or how they affect your system. A lot of times if you're having stability problems, the best thing you can do, if you don't think it's anything with your loop, is do what I just did right here, and that's go in and change the time step in your system. Most of the time, if you bring that down to a very, very low number, you can get rid of a lot of the instability issues. So, okay, I'm going to close that out now. And we'll have some more opportunities to play with this in some of our next lab examples. Let's talk a little bit about modulation. So we have our voltages that are generated by the output of the field-oriented control algorithm. What do we do with those? In the simple example that we just used, we would actually just put that into a PWM module and generate sinusoidal PWMs, and that was good enough. But there are other modulation techniques which actually offer some advantages that we might want to consider. And one of the most prominent ones that's used today is called space vector modulation. And we'll talk a little bit about how that works as soon as I get my clicker working here. There we go. So with PWM, when we're generating PWM voltages for a three-phase machine, we essentially break the problem down into three separate control problems from a modulation point of view. And that is, what do we need to do? What is the algorithm to generate the PWMs for phase A? What about for phase B? And then also for phase C. With space vector modulation, we throw all that out the window. And instead, we look at the inverter as a giant state space machine, essentially. Okay, it's basically a sequencer. So looking at it that way, we have some kind of system that has 6 binary inputs, and that would be for each transistor, it can be on or it can be off. So how many possible states can we put the inverter in with these 6 inputs? That would be what? 2 to the 6th power, which would be 64 possible states that we could put the inverter in. But we're going to throw most of those out right away because they do nasty things to our inverter, such as a top transistor and a bottom transistor being on at the same time. That's a no-no because you end up creating something called shoot-through current and you end up blowing out your inverter. So we're going to only use a subset of those 64 possible states that we can put the inverter in, and those are shown here. We're going to divide up the 8 remaining states into 2 categories. There are 6 states, or voltage vectors, if you will, that actually generate voltage on the motor winding, and then there are 2 states that don't generate any voltage on the motor winding. In that case, we'd have all bottom transistors turned on or all top transistors turned on. Okay? And you can actually see those states represented here in this animation, which shows as I go through step 1, step 2, step 3, how that affects the switches on the output of the inverter. Finally, step 6, and then the 2 null vectors, as we call them, which generate no voltage on the motor windings. So what we have is we have a situation like this. Again, looking at it from a space vector point of view, I would like to be able to generate a voltage of any angle and within reason also any magnitude so that I can generate these sine waves as shown here. But what do I have to work with? Well, I only have these 6 voltage states or voltage. This is what the voltage states look like on a space vector diagram. I've only got those 6 different states to work with as shown here. And if you look at it as I go from one state to the next, it looks like 3-phase square waves that I'm applying to the motor. So how do I go from a situation like this to being able to create any voltage at any voltage angle that I want it to be at? For example, let's say that I want to create a voltage vector of this amplitude. Instead of what's shown here, let's say I want it to be exactly 30 degrees. But my only options are every 60-degree intervals I can create a voltage vector. How can I do that? Any ideas? What's that? Do what between the two? Yeah, kind of modulate between the two. So if I wanted to generate a voltage vector of exactly 30 degrees, I would spend a certain amount of time in this voltage state and then an equal amount of time in this voltage state. And as I go back and forth between them very, very rapidly, like maybe 10,000 times a second, what happens is the motor feels that and averages it as a voltage vector which is exactly at 30 degrees. Now, what if I want to change that voltage vector? Instead of being 30 degrees, I want it to be 50 degrees. How would I change my control between these two states to cause that? Yeah. I just spend more time in voltage vector V3 than I spend in voltage vector V1. What if I want to create a voltage vector at 90 degrees? What would you tell me to do? Exactly. Now I've crossed a sector boundary. Each one of these represents a sector boundary. So once I crossed another sector boundary, now I modulate between two other vectors. And you can see if I do that, as I go around the space vector diagram, using all 6 of these states, I can create that voltage angle to be pretty much any angle that I want it to be, just by the averaging process, the averaging effect that the motor has on those waveforms. Now, let's take a look at how we're doing this. We see that the output voltage vector is created by repeatedly switching between 2 adjacent vectors. The amount of time we spend in each one of those specific states will determine what the angle is. But what about the amplitude of the voltage vector? How do I control the voltage vector amplitude? Don't forget, we've got those 2 other states, the null states. So we mix in a little bit of the null state, and that will then control the amplitude of the voltage vector. So now I have something where the output angle is determined exclusively by the relative on time between 2 adjacent states, but the output magnitude is determined by the relative on time of both of those states in terms of how much time I spend in voltage vector states versus how much time I spend in the null vector. And don't forget, we've got 2 null vectors to work with. We've got the case where all top transistors are turned on and the case where all bottom transistors are turned on. And we're going to use that to our advantage when we're deciding on these switching waveforms. Okay, so this is what a switching period looks like for space vector modulation. A certain amount of time that's spent in one voltage vector, a certain amount of time T2 that's spent in an adjacent voltage vector, and then a certain amount of time applying the null vector, which could be either V7 or V0, and that's T0 is how much time we spend in that. And then after that, the whole system repeats. At the next switching interval or switching period, we go back to V1, V3, V null. V1, V3, V null. And we do this over and over 10,000 times a second. And as the voltage vector is rotating, obviously we're changing the amount of time that we spend between each one of those. Those times right here are essentially modulating. And then, of course, if I jump over into another sector, it might be V3, V2 null, something like that. Now, here's a key part to understanding this. Do you think that the motor cares which order these vectors get thrown at it, that get applied? Does the motor really care what order all these different states come at it in? Not really. Mm-hmm. Yeah, I mean, the motor's just averaging them all together to generate an average voltage vector. That means if we want to, we have the ability to start messing around with the order of some of these different states to create some really weird, interesting switching patterns. Let me give you an example. Let's say that I run this one, V1, V3, V null, and then when I start my next period, I run it backwards. V null, V3, V1. Does that buy me anything? Is there an advantage to doing that? Less switching losses. Exactly. So now, whatever switch had to take place between the null vector and V1, I've essentially eliminated it. And of course, this is just a simple example of how you can combine states in different ways to reduce your switching losses on your machine or on your inverter. Because every time you have to change your state of your inverter, there's a small period of time where the voltage is transitioning through the linear region of that transition, of the transistor, and it's burning up a lot of power. So let's take a look at some different options that we have here. Now this is an example where every time I have an opportunity to apply a null voltage, I use voltage vector V0. All right? And the waveform looks something like this. So as the angle is modulating, as the voltage vector is swinging around, I actually generate phase to neutral voltages on my motor that look something like this. You say, gosh, those are ugly waveforms. Well, yeah, they are. The phase voltages are ugly. But remember, the motor only responds to line-to-line voltages. Assuming, of course, that it's a floating load and there's nothing else that, it's making any, it's not conducting to any other nodes, then the voltage that the motor is going to see is the voltage difference between any of its phases. And if you take any one of these phase voltages and you subtract one from the other to get a line-to-line voltage, a beautiful sine wave will jump out at you. So even though we're modulating with this ugly waveform, the motor sees a sine wave. Now, why do you think this might be attractive? Well, look at this. Between 0 and 120 degrees, let's go back to our space vector diagram. That would be 0, anywhere from here all the way over to here, through sectors 1 and sector 2. What we see is phase C is not switching at all. Its bottom transistor is just turned on and left there. The only things that are modulating are phase A and phase B. Finally, when we get to the end of 120 degrees, for the next 120 degrees, what we see is that phase A bottom transistor is just turned on all the time, and then phase B and phase C are switching and modulating. In other words, at any given time in this modulation waveform, I have one phase that's just essentially not switching at all. I have reduced my switching losses by 33% by applying this type of space vector modulation. And in fact, this is one of the types of SVM that we use with InstaSpin FOC to be able to reduce your switching losses. Okay? Now here's an example where I did the same thing, but instead of using, for null vectors, instead of using V0, I always use V7. This one is not as popular as this one because in most cases, especially if you have high side gate drivers that are charge pumped, they like to have a part of the signal go down to 0, periodically. So you're either PWMing where you're momentarily going down to 0 or you're all the way down to 0 all the time. In this case, when you hold the phase voltage high, with some gate drivers and with some inverters, eventually that high side charge pump, since there's no switching going on in that phase, the capacitor just bleeds off and you lose control. So that's why you don't see this one used quite as much, but this one is obviously a very, very important one. There's other variations that you can use, create different kinds of waveforms. In this case, I'm going to use null vector V7 in the odd number sectors and null vector V0 in the even number sectors. So this kind of mixes it up a little bit more, especially if you've got a local hotspot that's created by running your motor very, very slowly down to like 1 hertz or something like that. You may have one transistor that's turned on a long time and you don't get equal power sharing. So this kind of helps with that a little bit. But by far, the most popular space vector modulation technique is shown right here. And the way that this works is it's called the alternate reverse sequence. And what it does is it runs the sequence forward, and then the next time it runs it in reverse, and it alternates between using V0 and V7, back and forth. So let's take a look at what those PWMs would look like if we do that. Here is the alternate reverse sequence technique. And you can see, if you just look at the voltage states that I'm applying to the motor windings, this right here, phase C is high, phase B and phase A are low. That corresponds to voltage vector V1. And then at some point later, I switch to voltage vector V3, and then I apply voltage vector V7. All the way up to that dashed line, that corresponds to one space vector period. I start my second space vector period, and look what I do. I stay in voltage vector V7, but I run the sequence backwards now to voltage vector V3, voltage vector V1, and then voltage vector V0. So I'm alternating between V0 and V7 every time I have a null vector opportunity. So in this case right here, I have 1, 2, 3, 4 SVM patterns. Look at the PWM waveforms. And you can see right here, this right here corresponds to 1 PWM period. So the first thing we can conclude right away is that space vector frequencies are twice what your PWM frequencies are, which is kind of nice because it allows you to make changes in your control system within a half of a PWM cycle. And we see that used commonly, where, like let's say if you wanted to run your control algorithm at 40 kilohertz, but you only got a 20 kilohertz PWM, you could use space vector modulation to affect the front end of the PWM waveform differently from the back end of the PWM waveform by using SVM. So that's one nice effect of this. But there's something else that I think is interesting to notice here. What could you tell me about the alignment of those PWM waveforms? These are center-aligned PWMs. Now, there was a time when people thought that in order to do space vector modulation, you needed to have a special space vector modulator built up inside of your PWM module, which would actually do the vector rotation for you and everything else. About 1996, a fellow by the name of Pete Penevsky wrote a paper where he proved mathematically and also on a little 8-bit processor that no, you don't need a special space vector modulator to do SVM. All you need is a PWM module that can do center-aligned PWMs. And he demonstrated that if that is the case, then all of these other waveforms that I showed earlier, he can generate those using space vector, using center-aligned PWMs. That's all you need. And what was interesting is prior to that, you actually saw some semiconductor companies that had special SVM blocks in their PWM module, and then they just disappeared because people realized, oh, we don't need to do that. So here's what he pretty much concluded. This is taken straight from his table, or from his paper, and this is 1996. First of all, you define which type of space vector modulation you would like to do, whether it be the null V0, null V7, the alternate V0, V7, or the more popular one, the alternate reverse sequence. So which the expressions on how you calculate T1, T2, and T0. Assuming you know what angle that you want your voltage vector to be at, and assuming you know what the modulation index should be from 0 to 1, then you plug in these equations right here, and this right here, T is your total time, your switching period T, your switching period. You plug that in, and you can calculate what T1, T2, and T0 should be. Knowing those values, and also knowing what sector that you're in, then you can use this table to calculate exactly what values you drop into your PWM module. So you don't need any special space vector hardware or rotation algorithms or whatever to do this. It all just works straight off of straight center-aligned PWM. Now, there's another advantage besides switching loss capability or improvements that people get out of space vector modulation, and perhaps this is the biggest reason why people use space vector modulation, is because you can create sine waves that have a 15% greater amplitude than what you can get out of sinusoidal modulation alone. Now, what is it that determines the amplitude of how big our sine waves can be? Well, obviously, it depends on how big your bus is. If you have a 200-volt bus, you're going to be able to generate sine waves that have a 200-volt amplitude, right? But what we find with space vector modulation is we can take advantage of the fact, so let me just show you, as we're rotating that voltage vector around, you can see that's how big the sine waves are from one end of the bus to the other end of the bus. What space vector modulation does, though, is it takes advantage of the fact that really the greatest voltage difference that you're creating does not equal the bus voltage at any given time. So if we were going to take that into consideration, we should be able to create voltage vectors that are 15% bigger. Now you say, wait a minute, that's impossible, because when the voltage vector swings around so that it's right here, that would correspond to a PWM value of 115%. So how can you have a PWM of 115%? How can something be on more than all the time? Or in the case of the bottom end of the bus, how can it be off for less than all the time? It doesn't work, doesn't make any sense. Well, wait a minute. There's a trick that we can play here. And what space vector modulation does is it adjusts the common mode voltage for all three waveforms to allow you to do this, so that at any given time the voltage vector itself does not exceed the range of your DC bus. And let me show you how that works in this animation right here. What we're going to do is we're going to adjust this waveform, the whole space vector diagram. We're going to apply a common mode voltage to it so that it does something like this. See that? Now, in and of itself, this voltage vector that I'm generating is 15% bigger than this voltage vector right here. But because of the common mode voltage triangle wave that I'm applying to all three waveforms, it bounces that around so that you never ever have a situation where you're generating more than 100% duty cycle. Isn't that creative? So without any magical translations or boost hardware, boost converter hardware, or anything else, just inherently by how you modulate the waveforms, you can get 15% more amplitude than you can with just straight sinusoidal modulation. And that is a big, big effect for why people use this. Let's see it again in slow motion. This was done by a friend of mine at Freescale, and he actually put a lot of time in on this, so I want to give him credit for it. As we start the whole thing, you can see this is the common mode signal that we're applying. This is the effective sinusoidal voltage that the motor's seeing, but the actual waveform that the PWM module sees is obviously limited between 0 and 100% duty cycle, as shown here. That's how space vector modulation works. So we see space vector modulation being used a lot with field-oriented systems. The problem that you run into, if you remember when I showed in the previous example, how we calculate T1, T2, and T0, we assumed that we knew the angle of the voltage vector and the amplitude of the voltage vector. What do we have coming out of space vector modulation? We have VD and VQ, right? Or we have V alpha and V beta. But we don't have magnitude and angle. So what you could do is you could take the outputs of the space vector modulation, and you could do, what is it, essentially rectangular to polar conversion, if you wanted to. Or there's some other tricks that you can play using a special procedure designed specifically for rectangular notation. It's kind of a step 1, step 2, so on procedure. This is what we have used in the past when we do space vector modulation. And instead of going through and showing all the equations, I'm going to kind of blow through this because you can look at that at your own leisure. But it essentially involves finding out what sector you're in, and then once you figure that out and you've calculated the T1, or you've calculated T1, T2, and T0, then just going to the table for whatever type of SPM you want to use and putting those values into the PWM module. So again, space vector modulation works well with volts per hertz systems where you're just dealing with magnitude and angle, or it works very well with field-oriented control where you're dealing with rectangular coordinate representation of your voltage vector as well. Either way. Okay, so this is just a real quick little fun thing to do. In your exercise folder, you should find a file called svmswitching.html. Let's go ahead and open that up. This is not a VisSim simulation, but it's kind of fun. This was one of the things that I found online, which kind of shows how this all works. svmswitching.html. Now in my case, when I open this up, nothing happens because with my browser I get this little thing saying that I'm restricted from running any ActiveX controls. You might have to say allow blocked content. Click yes. And then what this should do now is pull up a JavaScript. Let me give it just a minute. There we go. Now this little JavaScript right here shows exactly what I was talking about. The tip of the red vector, that is your voltage vector. And you can click and drag that anywhere you want to see what the PWMs would look like, to see what the effective amplitude of the sine waves would look like. But more importantly, look at these little histogram bars that are on the space vector diagram itself. This right here shows you the amount of time that you're spending in that particular voltage state with respect to the other voltage states. So let's go back to the example where I said I wanted to create a voltage vector which is at 30 degrees. We said that we would want to spend equal amount of time in voltage vector V1 and voltage vector V3. Well, let's just see that. Let's go ahead and put that in here, right about here. That's about 30 degrees. And sure enough, according to these bar graphs, we see that 50% of our time roughly is being spent in this voltage vector, 50% is being spent in this voltage vector, and of course the null vector, which is right here close to the origin, that's an empty bar graph, which says we're not spending any time in the null vector. Now click that voltage vector. Try not to change the angle, but just drag it towards 0 so the angle stays the same. What do you see happening here? You see the amount of time I'm spending in the null vector is going up and up and up, but since the angle does not change, these two percentages don't change at all. In other words, in this case, I'm still spending about 25% of the time in this voltage vector and 25% of the time in this voltage vector. So you can drag that over into other sectors, and this little JavaScript will track that. And always keep track of the relative amount of time that you're spending in one of the voltage vectors, whether it be the voltage vectors or the null vector. So this is really, really neat. I wanted to show this to you in case, you know, when you get home, you actually might want to fire this up on your computer and let your kids play with it. I mean, this is like a video game. You can actually spin it around and around. Get your wife to get involved with it too. She might appreciate that. But surely you can see the value of how this can demonstrate what's going on with space vector modulation. All right. I talked earlier about the fact that with a permanent magnet synchronous motor, we'd like to take the d-axis current and set it to 0. And why is that? Because we already have a permanent magnet. We have all the flux that we need already. So why do I need to, to decrease the efficiency of my machine by applying more d-axis current? Well, believe it or not, there are times when in fact you would like to have something besides 0 as a commanded value of d-axis current. And that would be situations where you're trying to go really, really fast. You've got the motor going at its rated speed, but you actually want to go beyond rated speed. So let's say your motor is rated at, at 100 volts. It's capable of doing 3,000 RPM. But you say, no, I really want to jack that up to like 5,000 RPM. So how can I do that? Well, we can actually apply a negative d-axis current to what's called weaken the field that's seen by the stator. How does that work? Well, think about it. Any current on the d-axis is going to be directly in line with what the magnetic flux is generated by the rotor. If you have positive d-axis currents, you're actually enhancing the flux, probably driving it into saturation on your steel, okay? But what happens if you put negative d-axis current on it? It starts canceling out the rotor flux. Specifically, the amount of rotor flux that's coupled into the stator, you're now starting to reduce that. And as a result of that, it reduces or essentially changes the back EMF constant of the motor. So what was, your top speed now, because of the back EMF constant, you reduce the back EMF constant, and now all of a sudden you can go at higher speeds. And that's shown right here in this simple little example where I show a simulation where a motor is trying to get up, to a certain speed, but all of a sudden it reaches its top speed, and since the back EMF is so large, it's inhibiting the inverter's ability to create current to flow in that motor. And as a result of that, your torque just falls off, and that happens to be as fast as you can go. So how do you deal with that? Well, there's different ways that you can do that. And number one would be to create a lookup table where you've already gone out and characterized your motor, and some people actually do this. This is actually the most accurate way to do it, because you can tailor your field weakening effect with respect to your particular motor and get it exactly right. So in this case, you create a lookup table where you have some nominal value of ID. Let's say in the case of a permanent magnet motor, this value right here happens to be 0. All the way up to the rated speed, and then if you want to go beyond rated speed, you need to start applying negative d-axis current to counteract the rotor flux to reduce the back EMF effect so that you can actually go at those higher speeds. Okay, so that's one way to do it. We at TI don't do it that way because, like I said, that requires us having to go out and customize or tune this for every customer to get the field weakening effect to work a specific way. We use another technique which is based upon the voltage limit of your system. This is actually a feedback system, and the way that it works is we always give well, first of all, this right here is my voltage space vector diagram. So the limit, the circle right here, this is how much voltage I can have magnitude-wise. In other words, the radius of that circle is how much is my magnitude of my voltage vector, which, by the way, can be split up between the q-axis and the d-axis. So if we have a voltage vector right here of VD, that tells me that given the power supply that I have, which is my V-lim right here, the maximum amount of q-axis voltage that I could generate would be right here. So, VD and VQ of those values would put me right on the circle. So that's called the q-axis limit right there. The way that this algorithm works is when you're coming up with the limits, the voltage limits on your PI current controllers, those limits are dynamic. And the way that it works is you give the d-axis first dibs on the voltage vector. All right, because that's what determines how much you have to weaken the field in order to achieve a certain speed. So in most cases, when people are weakening the speed, they're not worried about efficiency as much as just being able to achieve that really high speed. So the d-axis gets first dibs on what this voltage vector can be. So what we do is we let VD be established to whatever it needs to be by the d-axis current regulator. From that, we can go up and define, well, here's how much current, or here's how much voltage is left over for the q-axis. That limit then, whenever we get to within like 0.95, and by the way, these numbers, you can change them to however you want. But when we get really, really close, when VQ gets really, really close to that limit, what it does is it kicks in this slewing algorithm, which all of a sudden starts applying more and more negative d-axis current. What that does then is the negative d-axis current starts reducing the back EMF effect so that that particular voltage, when applied to the motor, can now have the ability to generate some current. See, that's the problem. When you're up at a very, very high operating speed, when the back EMF voltage is so big, there's just not enough voltage difference between your bus voltage and the back EMF voltage to allow current to flow in your motor winding. We reduce the back EMF voltage by changing the back EMF constant, and that effectively then allows us to achieve these higher speeds. So again, this is kind of a dynamic algorithm which is running in real time, and we have the ability to turn this on or off. You can actually select that, like for example in InstaSpin FOC, whether you want this effect to be on or off. And this just shows an example of what happens when we do a field weakening. So the same motor, same analogy example that was running before, we saw that the motor was coming up to speed. Right here before it hit the previous speed limit, that's as far as it could go. But by reducing the flux that we see on the motor, we can actually, even though the torque starts falling off, we still have some torque. It's not completely zero, and that will allow us to get to higher speeds. Not very efficient because we are applying d-axis current, which doesn't produce torque, but it is burning up energy in the windings of your machine. But again, in most cases with customers, like if they're a washing machine application or whatever, and they want to go into the spin cycle, they're much more concerned about being able to get to that rated speed at that point than they are about the efficiency of the machine in most cases. Question?
So in an application, if you hit this limit before you have the flux weakening, you should see the current being consumed drop.
Yeah.
Effectively.
Right. Because for the q-axis regulator runs out of steam. It's applying all this voltage to say, give me more current, give me more current. But the back EMF voltage inside the motor is saying it's so high that the differential voltage that's across the winding, it just can't create any current. So you got to change that back EMF constant to bring that internal back EMF down. And that's how it works. Yes?
So if you're increasing the speed, this type of data is not something you'd find on a typical data sheet, correct?
No.
So how would you suggest reliability concerns, solving those, with the higher speeds, higher, just in general?
Reliability concerns or?
Everything.
Okay.
Yeah.
So
It's not data you would have, right?
Right. No, you're right. This is the kind of data that doesn't show up on a data sheet. I just repeated it. This is the kind of data that doesn't show up on a data sheet. So in order to do it, in many cases, if you're doing the lookup table approach, you have to do it empirically. So you're trying to go to a certain speed, and you just have to keep decreasing your D-axis current until finally you can get to that speed, under whatever load that you're requiring for that particular scenario. And then if you want to go faster, and again, following your load profile, in order to get to that speed, you might have to apply a different amount of D-axis current. That's how it works with the lookup table approach. With the voltage feedback approach, all we're doing is essentially saying, well, let's only apply enough D-axis current that we can create enough, that will allow us to create enough Q-axis voltage to be able to generate enough torque to go where we need to go. That's the way that it kind of works. Now, let's talk about the reliability aspect of it. If your motor is not rated to go that fast, you should probably talk to your motor manufacturer and just see if they have any data or field experience to say what happens when you run the motor that fast. Because you're obviously stressing the machine, your bearings, you're stressing, you're creating more heat and friction in your bearings by running it that fast. All those issues should be discussed with the motor manufacturer. And in most cases, they'll say, if you're not running it continuously like that, you're okay. The other thing that you run into, and this is something that we run into from a control point of view, when you are field weakened, you are essentially reducing the back EMF of your machine to allow your particular bus voltage to be able to drive that motor. Now, what would happen if all of a sudden something went wrong with your control algorithm or something froze up and the amount of D-axis current that you were applying now goes back to zero? Well, here's the problem. As soon as that D-axis current goes back to zero, your voltage, your back EMF constant, immediately reverts back to what it was before. Now you're going, let's say, twice the speed that you were going for rated voltage. You're generating twice as much voltage as your bus voltage now, which is going to be coming right back into your bus, and if you're not careful, you can blow out the bus caps, blow out your transistors. So I always tell my customers, when you're doing field weakening, that's a very precarious area to be working in, and you go slowly. You change things slowly. You don't want to cause transients, because sometimes transients can cause weird effects, and next thing you know, you might be in a situation where you're backfeeding voltage into your bus. So, any other questions about that? Where's my clicker thing? Here it is. This is just kind of a subtle point that I'll ask you, and I'm guessing that it's kind of a trick question. True or false? On a permanent magnet motor, the rotor flux must be decreased in order for field weakening to occur. Now, based upon everything I just said, you'd probably be inclined to say, well, yeah, that's true. We have to reduce the rotor flux. Believe it or not, the answer is false. When you do field weakening, you do not change the rotor flux. All you do is change the rotor flux that couples into the stator coil. That's where the field weakening occurs. So many people believe that when you field weaken, you actually are reducing the flux that the magnets are putting out. No. The magnets are already magnetized to give you a certain amount of flux. You're not changing that. What you're doing, though, is you're bucking that flux that couples into the stator circuit. And that is what causes the back EMF, and that is the flux that you're trying to reduce. Okay, so it's just kind of a trick question. I had a lab exercise built around that, but I think I'm just going to go ahead and skip that for now, because I want to get to, this I think is a much more interesting topic. So take a look at this diagram right here. Now this is, without getting uber technical about this is a synchronous frame model or algorithm representation of a stator coil. And it's, whether it's an AC induction motor or whether it's a permanent magnet synchronous motor, or even if it's an interior permanent magnet motor, they all have exactly identical this topology right here, where all you're doing is filling in the parameter values, like what is the stator resistance, what is the stator inductance. And this diagram right here then defines how your stator circuit is going to work. This is kind of like the Rosetta Stone, okay? If you understand this, then you can understand a lot of things about how motors work. And what we're going to do in this next example is we're going to take this diagram right here to figure out how can we design current regulators that have axis decoupling. We haven't talked about that yet. But here I want to show you something. When you change your Q-axis voltage right here in an effect or in an effort to change the Q-axis current, look what happens in the middle of this circuit right here, in the middle of this diagram. There is this cross-coupled term right here, which is dependent upon the speed that the motor is going, and it's also dependent upon your Q and D-axis stator flux inside the machine. So when you make a change on one axis, let's say that I make a change right here to change VSQ to be something different, and it happens very rapidly. Well, guess what? That couples into the D-axis as well, and you can create this little spike in the current on the D-axis. Well, this is obviously undesirable. When you change something on your Q-axis current regulator, you'd like to have it affect just the Q-axis. And also for the D-axis, the same thing. So what we're going to do now is, first of all, we're going to go through and write the equations which define how the stator circuit works in just about every motor. We're going to identify the cross-coupled term, and then we're going to cancel it out with feed-forward compensation. And then we're going to finish the whole thing up with an exercise in VizSim that shows how effective this technique is. Okay? So let's do that. I'm going to do this first, and I'll try to use this whiteboard right here so we can see it. And I'm going to write the equation which defines the D-axis right here. Now, first thing you notice, the D-axis has an integrator in it. So right away that tells you it's going to be a differential equation. All right, we have to take that into consideration. Let's just start all the way at the left-hand side. VSD equals. What does it equal? What's the first thing that happens to it? The IR voltage drop occurs, right? So VSD comes in. The first thing that's subtracted off is the IR voltage. I'm just going to do the voltage loop around the circuit, if you will, and just define an equation. So it's going to be ISD times what? Times RS. Okay. Oops, wait a minute. I'm sorry. I'm not doing this right. Let's do it this way. VSD minus, there we go, ISD RS plus this term right here. What is this term? This is equal to the speed, omega E, that's the electrical frequency, times what? The stator flux, right? The Q-axis stator flux. So it's going to be flux, SQ, all right? And then this whole expression right here gets integrated. So I'm going to take this, integrate this expression, the whole thing, dt, integrate it with respect to time, and then I'm going to subtract out the back EMF constant. Let's do that on the second line here, minus KE. And now I'm at this node right here. What does that equal? Well, I'm going to work backwards now from this. I'm going to say it's equal to ISD times my stator inductance. That's equal to ISD times LS. I think I got it. So now I have this equation right here for the d-axis, which includes the d-axis voltage, and it also includes the d-axis current. Now we can make a substitution here. Let me back up. First thing I want to do is, since I've got this the whole side over here is integrated, I want to move this over to this side. So I'm going to put plus KE here and get rid of it over here. Okay, as shown. Now, I want to take the derivative of both sides of that expression. And what do I end up with? I'm going to end up with VSD minus ISD RS plus electrical frequency times the Q-axis stator flux is equal to, and then we'll take the derivative of each of these terms individually. What's the derivative of a constant? 0. What's the derivative of ISD-LS? That should be pretty familiar. LS di over dt. Recognize that? L di dt? That's the voltage drop across the inductance, essentially. All right. So now I've gone from this to this. And I'm going to also make the substitution for the for the Q-axis stator flux, which is this term right here. What is that in terms of Q-axis current? Well, it's actually equal to ISQ times LS, right? And that'll give me the stator flux. So I'm going to do that substitution right now. Instead of right here, I'm going to put ISQ LS. There we go. Now this looks like a perfectly normal differential equation where I have my stator voltage, my stator current, it's a resistance, I've also got an inductance, and everything you'll notice is on the d-axis except this term right here. I don't like that. It's messing up my system. It's cross-coupling from the other axis. I do not want any cross-coupling on that. So what can I do to get rid of that? Well, inside my inside my d-axis current regulator, I have something which is generating that signal, right? All I'm going to do is I'm going to, here's the output of my Q-axis or my d-axis regulator coming out. Here's my PI controller right before it. All I'm going to do is, since I know I'm going to have this cross-coupled effect in here from the currents that are feeding into my Q-axis and d-axis regulators, I'm going to subtract this term out. So I'm going to have another block right here, minus, and then I'm going to take this term right here and feed that in right there and subtract it out, and that should get rid of the cross-coupling then from the Q-axis back into the d-axis. Would you agree? Well, let's see if that's right. If you actually go look at the simulation right here, the correction voltage for the d-axis turns out to be the speed times the Q-axis current times the Q-axis inductance. Speed, Q-axis current, and Q-axis inductance, and right away, you see here it's a -1 indicating that before it gets combined with the d-axis voltage regulator output, current regulator output, I invert that so it essentially gets subtracted from that. And I have now designed a decoupling network based upon the differential equations for that stator, which will completely, essentially, cancel out the noise artifact in my current regulation that's caused by that cross-coupling effect. You see what I'm saying? All right, so now we've seen how to do this. Let me go back.
Can I ask a question?
Sure.
What just the relative size
that is very much dependent upon a lot of different effects, like your component values, your parameter values. But right away, you should be able to answer that question. I forgot to, the question was, I forgot to repeat the question, is how large is this coupling effect on your regulator outputs? It depends on a lot of things, but you can look at this right here to see one thing that it's very, very dependent upon, because the cross-coupling terms both get multiplied by speed. So obviously, as you're going faster and faster, that's when you see any change on one axis starts coupling very, very heavily into the other axis. And if you're not careful, it can actually start causing instability as these two axes start talking to each other through the motor windings. Okay, so yeah, it can be a big deal. In some motors, it's not a big deal. The example that we're going to show you, though, in the VisSim simulation, you'll see that it is a big deal. Okay? Now, so what I did was I came up with the cross-coupling term that I'm subtracting out for the D-axis controller. What I'm going to do, and you're going to love this. What happened? Don't die on me. Yeah, shake it. Here, it came back. I think I hit something on my, that's what I hit something on my mouse. It scared me, man. So I did this for the D-axis. I found out what this cross-coupling term was that's coming in here, and I effectively subtract this out right at the output of the D-axis current regulator. I'm going to pass out some paper, and I want you to do exactly what I did here for the Q-axis. In other words, you figure out what the coupling term is into the Q-axis, also come up with that term that should be subtracted out on the Q-axis controller, and then we'll compare results and see how you did. Okay? Does that make sense? There we go. You hopefully have a pen. If you don't, there's a whole basket full of them back there that you can get. There you go. Do you understand what I'm asking you to do? Does it make sense? All right. What's that? Yeah, just do it for the Q-axis, right? Just change the D to a Q. Not quite that easy. You'll find out why. But that's a nice try. Very nice try. How are we doing here? I got 3. Actually, we ran out of paper. So, sorry, you guys don't get to do the exercise. I'm sorry. We don't have enough paper. Gee. So I'll give you maybe 5 minutes to do this. First thing you want to do, write the voltage expression for that particular axis, including the cross-coupled term. Make sure you get that. Do the substitution of that stator flux for that particular axis in terms of what it equivalently would be if it was the current, not just the flux, but take the inductance and the current, and then find out what that term is. And essentially, once you find out what that term is, you subtract it out, and you've got your feed-forward compensation for that axis. And then we'll do it together. One point to consider, a lot of people ask me if this is a typo, and I assure you that it is not. The fact that this flux comes in and is added to the d-axis voltage. This flux comes in and it's subtracted from the q-axis voltage. How we doing? You got something already? All right, let's work on it together and see what we come up with. Is it okay if I erase this now? Okay. Okay, now we're going to do it for the q-axis. So what do we start with? VSQ. What's the first thing that happens? Minus ISQ RS minus, let's do it in steps here. So it would be the speed, omega E, times the stator, the d-axis stator flux. So it would be flux SD. Okay. And then all that then gets integrated. So we got to put parentheses around this and this. Put a little integrator sign over here. And then put dt right here so we don't forget where the end of our integrator is. Okay. And then we have that expression is equal to ISQ times LS, right? Yep. Okay, so we're all together so far. Take the derivative of both sides. VSQ minus ISQ RS minus omega E flux SD equals LS d ISQ over dt. All right? Standard differential equation for the q-axis. Here's this cross-coupling term. So let's find out, first of all, I'll put a little minus sign there. What is flux SD? Well, unlike the way it was on the q-axis, we now have this other term in here, KE. So the way we handle that, we say flux SD equals what? ISD times LS plus KE. Right? Yep. Flux SD, if I move this over to here. Yep, okay. So now what I'm going to do is this right here is the term that annoys me. I'm going to take and plug it back in up here, and what I end up with is this expression right here, omega E times ISD LS plus KE. This term right here is subtracted from my voltage on my Q-axis. So what I want to do to compensate for it is I take this, and whatever my regulator output voltage is, I'm going to add that term to it. Is that what you guys got? Wow, you guys are smarter than I thought, because a lot of people don't get that. They forget about this KE effect right here. So if we go ahead, if we jump ahead and look into this diagram right here, this is indeed what we actually see. This is the compensation term, just like we calculated it before. And you can see how the speed gets multiplied by the addition of those two terms right there, just like that. We're going to run a simulation and show how effective this is with and without coupling added. But I want to bring your attention to one thing right here. Do you remember what I said earlier this morning? I said that if you're dealing in SI units, that Weber's is exactly equal to your back EMF constant in terms of volts per radian per second. Now look at this. Right here, I have this flux SD. And so let's go ahead and say that this is, we're going to make that translation. This is my back EMF constant. All right? So my back EMF constant, which is volts per radian per second, which gets multiplied by radian per second. In other words, what is this term right here that's being cross-coupled? It's the back EMF constants. In other words, it's not the back EMF constant. It's the back EMF voltages that are cross-coupling between both axes. In fact, when we do field weakening, this is what we're trying to get rid of. We're trying to reduce that amount of voltage on both axes so that we can have some left over to generate current to flow in our loop. So it's essentially, my point is, once you understand the Rosetta Stone of how a motor works, then all of a sudden all these obscure processes and equations and everything else is like, oh yeah, that makes sense now. I can understand exactly why the compensation, the cross-coupled decoupling algorithms work the way they do, or why the back EMF constants, when I'm trying to do field weakening, why that works the way it does. It's all here. This is it. All right. Let's try this out, and what I'm going to do, let's move ahead, and let's see, is this using the... Okay, we've already done this part. We did this calculation. Now, what I'm going to do is I'm going to ask you to open up in your lab exercises folder. There is a file called, let's see, where is it? Okay, FOC with encoder.vsm. So go ahead in your lab exercises folder, open that file up, and we'll see how this works. Now this is a little bit more of an involved simulation. It has lots of different things going on in it. And you can actually see, like there's field weakening, which is going on over here in this block. But what I want to draw your attention to is right here. This is the Q-axis, or this is the D-axis current controller. Here's the Q-axis current controller. And you can see, if we open up either one of those, the output of the regulator, besides the P and the I terms, there's also this V-comp term, which comes in as an input. Where does that V-comp term come from? It comes from this decoupling block. And you can see that right here, in this area, that is where the compensation is taking place. That is exactly the equation that you guys solved for the D and the Q axes earlier. Okay, so that's what we're going to be using. Now, what I want you to do this time is the directions say one thing, but I think I can actually illustrate this principle better by using a different motor. What I want you to do is in the lower left part of the page, I want you to double click on that block that says motor load selector block, and go ahead and open that up. So let's do that together right here. Now with that open, I don't know what yours is default set to in terms of a motor, but we're going to select a different motor. And the motor that I want you to select It's the second option from the top for the Baldor BSM 90M motor. Okay, so what you do is you go here, pull this down, and you'll see a whole palette of different motors and loads to select from. So there's a whole bunch that say Baldor 200 volt. There's like 5 of them. And then you hit the Baldor BSM 90. Click the second one from the top. Click on that one. Okay? And then the second thing I want you to do is go over here to the current regulator decoupling enable field. Right now I've got decoupling enabled. I want you to turn that off. That means we're not going to use cross-coupling compensation. We're just going to let the regulator run by itself and see what would happen. Once you've done those two things, click OK, and what you should see is the title of that selector block now. It's going to pull in a bunch of parameters for this, which is the Baldor BSM 90M 2150 permanent magnet synchronous motor servo motor used in a pump application. So I'm pulling in parameters for the motor. I'm also pulling in parameters for the load. All right. Now, let's go. I've got some profiles, some speed profiles and everything already laid in. Go over to the section where the graphs are, to the right-hand side, and make sure you can see the second from the top graph called speed. Go ahead and click the green run arrow, and let's watch this. So you can see the commanded speed versus the actual speed. It goes up to about a little over 1,000 RPM. Then I ramp it up very nicely and evenly to 4,000 RPM. And then at 4 seconds, I slam it back down and say, no, I want you to go now back to 1,000 RPM. And you should get a graph that looks something like this. But let's scroll down and look at the D and Q currents that were used to create this scenario. Can you see that? So toward the bottom, there's going to be a graph that says D-axis current, and then right under that is a graph that says Q-axis current. Look at the transient that's caused on the Q-axis, because remember I said I want my motor speed to change instantly. I want it to go from 4,000 RPM to 1,000 RPM as fast as you can go. So right away the motor hits the simulation hits the current limit of how fast or how much current it can apply. And that looks like it's about, what, minus 20 some amps. That creates a huge transient on the Q-axis current, which bleeds over into the D-axis current. Look at that thing. In other words, my commanded value of D-axis current was the green waveform. Look what happened to the actual waveform. Do you see that? Are you guys getting the same effect that I'm seeing here? Okay. Now, go back over to the motor load selector block. All I want you to do is change that field that says current regulator decoupling. I want you to enable that now by putting a 1 in that field. All that it's going to do is in this decoupling block right here, it allows these compensation voltages to reach the respective current regulators. Before I had it blocked with that merge output right there, which says, if it's not turned, if that field is 0, then just don't let it get out there. All right. So now that that's turned on, let's run this again using the compensation, I should say the decoupling algorithm that you guys designed from looking at the stator circuit. Run the simulation again. Once again, look at the D and the Q currents. Notice I am doing field weakening right here, by the way. What do you see? Hopefully you should see that the commanded value of the D-axis current and the actual value of the D-axis current are pretty much identical now, or at least tracking much better than they were before. Also, that oscillation effect that you saw between the D and the Q axis on the current waveforms is now gone. You've essentially broken that link because you're directly compensating for that. Is this what you get? Is something that looks like this? Think about what you guys have just done. All right, you designed a decoupling network. It worked. You're using feed-forward compensation in tandem with feedback to get the best of both worlds. We still have negative feedback on our Q-axis current regulators, but we're using feed-forward to completely cancel out a noise effect, which is caused by the coupling inside the motor. You can't change that, but you could doggone sure can fix it by putting in exactly that same amount of signal to drive the total effect back to zero. And that's how you do axis decoupling. But again, it all stems back to understanding what is that stator circuit and how it works. I'm sorry, I think this is exciting stuff. I mean, when you can actually do that, you can look at the circuit, you can say, I know how to write that differential equation. I know how to apply that as a cross-coupling feed-forward term. I mean, you guys are motor control experts now. So, all right. So enough of the platitudes. So just in summary, this is what we have. Put it all together, it looks like this. You should recognize the series form of the PI regulator for the D-axis, the PI regulator for the Q-axis, and then in between these terms right here generate the cross-coupling voltages which exactly cancel out the noise that's created by the coupling inside the motor back in the, further back in the diagram. That's essentially what we're doing. All right. Let's go a little bit more, and then we can take a break. Maybe sometime around 2 o'clock, I think will be good, if that's okay. We talked about field-oriented control right now of permanent magnet synchronous motors. What about AC induction motors? Can we do field-oriented control with that as well? Well, the obvious answer is yes, we can. But because the AC induction motor the topology is different than a permanent magnet motor, there's obviously some things that we need to take into consideration in order to make our field-oriented loop work correctly. So first of all, let's take a look at the speed-torque curve of an AC induction motor, which is quite a bit different than the speed-torque curve of a permanent magnet synchronous motor. The way that an AC induction motor generates torque is by something called slip. And what that means is if you look at how fast the magnetic field is spinning around the stator of your AC induction motor versus how fast the rotor is actually spinning, you'll see that they're not spinning at the same speed. And that difference in frequency or that difference in speed is called slip. And the more slip you get, typically you get more torque. And that's measured right here on this axis, which shows that this is a plot of the percentage of synchronous speed that the rotor is actually running at. So let's say that the rotor is running at exactly the same frequency as your stator flux frequency is running at. Well, in that case, you're generating zero torque. Now, why would that be? Well, think of it this way. An AC induction motor is I've heard it referred to as a rotating transformer. And effectively, that's what it is. Now, think about this. You've got a transformer that has a primary and a secondary. And it's rotating, all right? Now, if, let's say I'm applying 60 hertz to the stator coil, that'd be like applying 60 hertz to the primary of the motor. Now, if the rotor is spinning at exactly the same speed as that applied stator frequency is, what is the frequency that you think the transformer sees? Zero. Okay, because it's spinning at exactly the same frequency, so there's no difference there. The stator circuit sees exactly 0 hertz. Now, on a transformer, if you apply 0 hertz to the primary, how much current do you get on the secondary? Well, besides transient effects, you get nothing. So we have under those conditions, we have no rotor flux. So it can't generate any torque because we don't have any rotor current. But now, let's say that your applied stator frequency is 60 hertz, but your rotor is spinning only at 59 hertz now. Now what frequency does the transformer see? sees 1 hertz. Well, that's enough that you start getting some current to flow, and as a result of that, you start generating a little bit of torque. And you can see as the rotor starts slowing down more and more to 58 hertz, 57 hertz, 56 hertz, or whatever, you keep generating higher and higher torque until finally the parasitic effects inside the motor start affecting how much torque you can generate. If you slip even further, all of a sudden your torque starts going down. This point right here is called the pull-out torque. And in most cases, you don't want to operate your load line right up close to that pull-out torque because you stand the risk of going over the edge, and that's how you stall a motor. If you have an AC motor hooked up to a line and you put too much of a load on it, what happens? It immediately goes down to 0 speed, or it stops spinning, and then it just kind of grunts or growls at you until it burns up. Okay, but even at 0 speed, you still have a little bit of torque that's being generated, and that torque, of course, is called the starting torque or the startup torque. Now, what do you think would happen if the rotor, let's say that the stator frequency is 60 hertz, but the rotor is spinning at 62 hertz? Now, what do you think the speed torque curve would look like? It's going to go the other way, right? In other words, we are going to continue at speeds which are higher than our synchronous frequency with a curve that looks something like this. Now, this is interesting because think about this. This is a speed torque curve, right? What is speed times torque? Does anybody know? It's power. All right? So we have positive speed, but we have negative torque. What does that mean? It's generating power. In other words, my AC induction motor has turned into an AC induction generator. And it really does work. I've had people say, well, wait a minute, there's no way that an AC induction motor could be a generator because it doesn't have a permanent magnet in it. It's like, well, that's not true. If you excite the field on an AC induction motor, as long as the field is excited, you better believe it can act as a generator. In fact, I was out in California, I think it was San Jose, and up on one side of Highway 1, if you look up into the hills, they have this whole windmill farm up there, a big bunch of just wind generators. So I went up there and I talked to the guy who was running the site that particular day. And I said, well, if it's not proprietary information, could you tell me what kind of generators that you're using in your windmills? He said they're AC induction motors. I said, really? How does that work? He said, well, we have this thing called an anemometer, and it measures the wind speed. When the wind speed gets high enough that we've calculated it would want to drive the propeller faster than it would normally go just by hooking the motor up to the grid, then we actually hook the motor up to the grid. So the motor then comes up to speed as a motor, but then the wind pushes the propeller to drive it even faster than the synchronous frequency of the grid. And as a result of that, power starts coming back into the grid because of this negative torque effect that we see right here. And that particular day, I think he was generating 3 megawatts of power with all these little windmills that he had up there, which he said, on a good day, a real windy day, he can get up to 50 megawatts of power. So in just about every case, it was AC induction motors. Now, AC induction motors are not the most efficient generator, but they represent the simplest control system because all you're doing is you've got an anemometer, check the wind speed. If the wind speed's high enough, 3-phase contactor, ka-dunk, throw it on the grid and just let it go. The slip regulates the rest. Unless, of course, the wind speed started getting so high that it would drive you up into here, in which case you'd have to do something to turn the propeller to a safe state or something like that. But oh yeah, AC induction motors, very nice generators. And if you don't believe me, take an AC induction motor drive and then try to slow it down really, really fast. Okay, it's going at some speed and all of a sudden say, now I want you to go at a much lower speed. And watch what happens. If you don't have adequate protection on your DC bus, you can blow a bus cap and a lot of other nice, nasty things can happen. All right. This is a neat little animation that I found online. It's from Mahmoud Riaz. He is a professor he's in the electrical engineering department at the University of, University of Minnesota in Minneapolis there. He's got a whole bunch of these kind of animations. He's got a whole website devoted to these kind of animations. If you just Google his name, it'll take you to his simulation page or his animation page, and all kinds of good stuff like this is up there. What he shows here is he shows a lot of the dynamics of what's happening inside of an AC induction motor. let's take a look at that. So here we have a voltage which is being applied, and pretty much the voltage vector is going to be right in line with this blue vector right here. And that voltage vector is going to create a flux vector which is 90 degrees, because remember, what is voltage? Voltage is d flux dt in a rotating machine. So that means that it's going to be, what, basically 90 degrees off when you do that integration versus what the other term is. So if this is the voltage waveform right here, the blue waveform, the flux waveform is going to be 90 degrees off from that, lagging 90 degrees. This is my stator flux right here, which is flowing in the motor, and you can see that stator flux crosses into the rotor structure. Now here we have a bunch of rotor bars. We can see the cross-section of those rotor bars as they go down inside the page. And you can also see the direction of current flow. A dot means that it's flowing out of the page, and X means that it's flowing into the page. So here's what happens. You see this little flux right here from the stator? It's cutting across the rotor bars. The reason for that is because the rotor is moving slower than the stator magnetic field. So I have slip. That slip effect causes that magnetic flux from the stator to cut across the rotor bars, obviously in the rotor. When that happens, you have d flux dt, which is voltage. So that means from one end of the rotor squirrel cage to the other end of that bar, you've got a voltage now that's developed across it. And that's going to cause current to flow, which is proportional to how big your voltage is. So obviously, the most current is going to be flowing right here where this is cutting through the most. Because if you look at this gradient right here, this is where my magnetic field of my stator flux is the greatest. So I'm getting more d flux dt right here on these bars, which are being cut. Therefore, the amplitude of the current, which is represented by the size of the circle, is greater. And that current flows out of the page, back into the page. Now, because I now have currents flowing in the rotor is going to create its own magnetic flux. And this is shown by this little green arrow right, where is it? The pink arrow right here. So here's now the rotor flux, or the rotor current vector, that's being formed. Now, when that rotor flux occurs and is trying to couple back into the stator, remember the stator flux is defined specifically by the voltage waveform on the motor. So if I have a sine wave of voltage applied to the motor, the relationship between the motor voltage and the stator voltage and the stator flux is d flux dt again. So that means when this other flux from the rotor comes in and tries to mess up that flux and change the level of the flux, if the voltage waveform in the motor doesn't change, that means the stator flux has to stay the same. So how can that be? Well, here's what happens. To keep the stator flux exactly balanced in relation to Faraday's law, remember d flux dt, the stator generates a counter MMF, if you will, to completely cancel out that rotor flux that's being generated right here, the rotor MMF. So that the result is now I have two currents which are flowing in my stator circuit. One is the current, this green current, which is generating the flux. The other one is a real current which is counteracting the rotor MMF, so that I have now a quadrature component of current and a real component of current with respect to the voltage waveform on the stator. Okay? And again, when you look at a stator, the representation of an AC induction motor coil, you'll be able to see these two currents right here. What happens when it's a generator? Well, it's the same effect. Nothing has changed in terms of the physics of what happens here. The only difference is that, look at this. The rotor is now spinning faster than the stator flux vector, which means that the d flux dt is in the other direction. So what used to be positive ends of the rotor bar now become negative ends of the rotor bar. What used to be positive current now becomes negative current, and now what happens is the rotor flux that's being generated is exactly, let's see, where is it here? This would be the, here, this is the stator current. Okay. It goes exactly the other way. So now what we have is we have a situation where we have the same magnetizing, darn it, right in the middle of my animation too. I think it just died. Okay, it died. So let me finish what I was talking about there. The d flux dt is in the opposite direction, which means the current flows in the opposite direction, which means now what happens is you have a negative current which is flowing with respect to the voltage vector. Okay? In other words, the current waveform now will look like it's almost completely inverted. So if you have a sine wave of voltage, but then you have a sine wave of current that's almost upside down from that, in every case now you have negative power, and that's what's coming back then into your grid acting as a generator. Okay? So again, nothing changed in terms of the physics of it. It's just that the d flux dt changed its direction. Let's take a break, because we were forced to take a break right now. I'm going to swap out computers, because I've got the presentation loaded on Richard's computer. And then we'll come back maybe in about 15 minutes, and we'll continue from there. How does that sound? Okay? Thanks.